This is the video for Unit 7, Lesson 2, Graphing Logarithmic Functions. The goal is going to be to identify key features of log functions and to graph log functions using properties that we've learned already with transformations and properties with exponential functions. So when we're graphing a function, again, log base b of x, a couple things we're going to notice. So we're talking about when b is greater than 0, and then x is greater than 0. So we've talked already a little bit about how you can't evaluate a log that's negative. So we're going to see that comes into play when we look at the graph. So an example we have here, it relates actually to the inverse function. So 2 to the x is what we did in the last unit. What we're focusing now is this log function. This is the inverse. Log base 2 of x is the inverse, right? So it's reflected around y equals x. It's like doing the operations, the reverse operations. And so the properties are going to be kind of similar. So when we did y equals 2 to the x, for example, we had our domain, and if you remember, it looked something like this, an exponential. We had our domain, we had our range, which had to do with the horizontal asymptote, right? So the asymptote would have been at 0, and then we would go from there. The inverse is actually, if you remember back from previous units, is the reverse of that, right? So our domain for our log function, you can see it actually has a vertical asymptote, right? That green line isn't going to cross the 0. So it actually has an asymptote at x equals 0. Instead of a horizontal one, you could see it switched to a vertical. That actually affects the domain. So you can see it goes from 0 to infinity. And then the range is going to be all real numbers. So these actually flip-flop because it's the inverse of 2 to the x. We're going to see that the x-intercept, it does have an x-intercept at 1, 0. And we're also seeing that we aren't going to have a y-intercept, so there's no y-intercept. For our end behavior is going to look a little bit different, but the same concept that we're maybe used to seeing, right? So we can see when I look at my left tail, and again, I'm just focusing on the blue graph. I'll even kind of get rid of that red one. When we look at our left tail, you can see it's going downwards, but it's never getting past that 0. So it doesn't go all the way to the left. You can see our domain goes from 0 to infinity, right? So that kind of comes into play. And when we look at the left tail, it goes to negative infinity. When I go on my right tail, it goes to positive infinity. So it's like the reverse of what we saw for 2 to the x. Identifying key features. Again, you're going to find with these, all of these have the same exact range. So the range is the same for all of these. So all of these are going to have a range of negative to positive infinity. They have a vertical asymptote. So this one has 1, you could see at positive 1. This is our log. And that's going to come into play in the domain. So 1 to infinity. We're going to see what 1 and infinity come in the end behavior. And then when I look at the left tail, it goes down. When I look at the right tail, it goes up. Same thing for the next one. If I look at, I do have a vertical asymptote at x equals negative 4. So my domain goes from negative 4 to infinity. My range for all of these is all real numbers, right? And then I can use that domain to help with the end behavior. So when I go to negative 4, when I go to infinity, when I go to the left, it goes up. When I go to the right, it goes down. And that's it. So very similar to exponentials. It's just the inverse, so the properties are flipped. When we talk about transformations, lots of different ways that you can do this. I'm going to show it using a calculator, but you can use it a lot of different ways. You can plot a parent function of a log and then do the transformations on the graph. You can do transformations on the table. I'm going to show it with the inverse function, but again, lots and lots of ways to do the same exact type of problem. So if there's another way that you prefer doing it, you could do it that way too. But I'm going to use the inverse in the calculator for these examples. So same deal that we saw before. Our A value, our A, H, and K does those same things it's always done, right? Our A can reflect a graph. It can also stretch or shrink. So nothing new. Our H can move graphs left to right. And remember, you always take the opposite because the subtraction is part of the formula. And the K can move it up and down. Okay, so now when we go ahead and do this, lots of ways to do this. I'm going to replace this with y. You don't have to. You can leave it as f of x. And really what happens is this is the same as the graphing the inverse and flipping the value. So I'm going to show this just because it might be a good skill to go over because you'll see it later for solving. But again, many ways to do the same problem. So if I want to find the inverse function, I'm first going to switch my x and my y. So I'm going to rewrite it as log base 4 of y plus 1 is equal to 2, or plus 2. If I want to find the inverse, I'm going to get y by itself. So I'm going to subtract 2. I have x minus 2 equals log base 4 of y plus 1. How do we undo a log base 4? And we're going to see this in later sections too. I'm going to raise it to the 4th power. Or I could just simply do the rewriting we practiced. So this is now 4 to the x minus 2. This goes away. I get y plus 1. And now I'm going to go ahead and subtract 1 now. So if I go ahead and subtract 1, we're going to get here 4 to the x minus 2 minus 1. Okay, so this is what we just found was the inverse. Now what we can do is we can actually use some cool features on our calculator since we now all have a graphing calculator. So I'm going to go to my calculator. I'm going to hit y equals, and I'm going to type in the inverse function here. If I type that in, I have y equals, I'm going to raise 4 to the x minus 2, arrow out, minus 1, and then I'm going to do second and graph, and I'm going to look at my table feature, right? I got a lot of crazy values here, so I maybe want to go ahead and scroll to be some values that are a little nicer to work with. I also want to make sure I'm able to graph them, so I might want to pick some values like right in the middle. So maybe I have here 1. So if I copy these values back down, I'm going to have here 0 and negative 0.94, 1 and negative 0.75. I had 2 and 0. I had 3 and 3, and 4 and 15. So if I want to graph my original function, which was this one right here, I could just simply flip it around now. And now this would be what I can plot. One thing to note, our asymptotes are always x equals h is always going to give you your vertical asymptote. So my h value, you can see, is actually a negative 1. I'm going to go ahead and plot negative 1. And then plot all these out. So negative 0.940, and then I got here 0.791, and then 0.2, and then 3.3, and then 15.4. So I'm going to go ahead and graph this, and this would be my log function here. You can see the original would have 1 through 1, 0. So another way you can do this is you could take your 1, 0 and move the points. That's another way you could go about graphing it. For the next example, it's pretty much the same thing, right? So we're only going to do one more example. I'm going to show it again with the inverse, but again, if you wanted to use a different method, you can. So I'm going to rewrite this. I'm going to replace the x and the y, right? So we have x equals 2 times the log of 3, y minus 1. I'm going to go ahead now and solve for y. So we're going to go ahead and divide by 2. I'm going to raise, to get rid of a log base 3, I'm going to raise it to a 3. I'm going to put a parenthesis here. So 3 to the x over 2 equals y minus 1. I'm going to add 1. And so my new equation is y to the 3x over 2 plus 1. So this is my inverse. And now I can go ahead and use my calculator to put that in. So like we did already, you just hit y equals. I'm going to go ahead and put that inverse in. So 3 to the x over 2. You can even do alpha y equals if you're more comfortable seeing x over 2 look like that. Or you can just do x divided by 2. That's the same thing. And then plus 1. And then second and graph. And that would give you your table, right? So when we go ahead and graph this out, I'm going to start, maybe I'll start at like -2. You know your asymptote is your x equals h. So this would actually be a +1 asymptote. So I'm going to go ahead and sketch that out. And then I have from that table -2 and 1.3, -1 and 1.6, 0 and 2, 1 and 2.7, and 2 and 4. So now to graph the original, I could just simply flip around those points. And now we would go ahead and graph this out. All right, so 1.3, -2, 1.6, -1, 2, 0, 2.71, and 4 and 2. And this would be our final answer. Right, so again, many ways to do the same problem. This was using inverses, but you can see the same transformations happen. So we moved over one, so it's like you took your parent function. It was also a 2, so that made it stretch out. If you have any questions, you can feel free to ask in class, sign up for T-Bolt time, or go to the center.